Okay, hello and welcome to another section in further mathematics. Today we'll be looking into the topic nature of graphs of a trigonometric functions. But before we proceed with what we have today, I think it would be nice for us to just take a review of our previous lesson. Okay, welcome back. You know, in our previous lesson, for the past few seasons now, we've been talking about nature of trigonometric functions, how they do appear. We talked about the usual so, ka, tua, where we went into enlisting that the word the S stands for sine, the C stands for cos, it stands for sine, this is cosine, and this is tangent. Today we are actually taking a good preview on the nature of the graph. Now, you discover as the trigonometric functions are being listed, there are some things they actually share in common, especially the sine and the cosine. And the tan is usually an extraneous function, in the sense that most of the functions, most of the attributes of the tan is gotten from a combination of that of the sine and the cosine. Okay, now, but let's bring back ourselves to what we have today. We are just interested in knowing the nature of the graph. That's the context is, if three graphs are being shown to you, how can you identify that of sine? How can you tell someone that this particular graph belongs to the cosine? Or how can you look at a graph and say, oh, this actually is a tan graph? Now look at the essential features of the graphs. Now the essential features of the sine graph. So we'll be talking about the sine graph. The first one to look into is called the sine graph. Now the essential features of the sine graph. Okay, let me say we have y equals to sine theta. If a graph like this is being plotted, what are the things that will make you identify that, okay, the graph you're seeing here is a sine graph or a cosine graph or a tan graph? The graph of a sine theta forms a wave-like pattern. It is said to be oscillate. Now when you talk about oscillatory motion is a motion that goes up and down, just like this, like this, like this, like this, continuously. This is what we call oscillatory, like the motion that comes off when you pluck a string. When you have a guitar and you strike it at one end, you discover that the string keeps moving this way. Oscillatory, up, down, up, down, up, down, up, down. And if you tie a rope, let me say at a point, allow the rope to be in this nature, get a hold of this, then vibrate it. You see the rope will be going this way, up, down, up, down, up, down, until you get to the place, generating a wave. So the graph of sine looks like an oscillatory motion going up and down, up and down, up and down. Now the maximum value of sine theta is 1, and it occurs at theta equals 90 degrees. Now the maximum value, if you plot this sine graph, you discover this is a sample of a sine graph that is shown in front of us here. This is a sine graph. This is a sine graph. One of the features is that the maximum value, look at, we stated something, the graph of sine theta forms a wave-like. Now this is the nature, goes this way, continuously, depending on the value that you have. Now, you know, maximum value is the highest point on the upper part of this. And the distance between the maximum displacement to this origin, naturally we'll call it the amplitude. And it's the same with this. You know, if you want to go by that point of maximum displacement, this place is called the crest, while this place is called the trough. So yes, so the point of maximum displacement the crest of a sine function is usually at +1, while the trough is usually at -1. Now, what's the difference between the crest and the trough? I stated it here. The crest is the point where the sine graph experiences a maximum value. This is -0.5, this is 0.5, this is 1. So this is the crest. So, and when it comes down in the lower part, at the point where this graph experiences the least value is -1, is called the trough. So if you're being asked maybe at any point, can you tell me the trough value of a sine graph? You tell them it's -1, and the crest value of a sine graph is +1. Okay, I've stated that it moves like an oscillatory motion, moving to and fro, up and down. Now the maximum value of it occurs at 90 degrees, and this point occurs when our theta is 90 degrees, while the minimum value occurs when theta is 270 degrees. So you get the trough at 270 and you get the crest at 90 degrees when theta is 90, and the distance from here to here is the amplitude. Same thing with this, from here to here is also the amplitude. This is also the amplitude. So this is the amplitude, this is the amplitude, this is a trough, this is a crest. So the crest occurs at +1, the trough occurs at -1. Now the minimum value is what occurs at -1. Okay, I've stated it here. The graph repeats itself at interval of 360 degrees. So the sine function is an example of a periodic function because it repeats itself at interval of 360. The function is said to have a periodicity of 360. Now what it's trying to tell us now is that the distance from here to here is 180, and from here to here is 360. That is to say, after 360, the graph, okay, let's assume we are bringing this point to this point. So you have something like this, up and down. So after 360, it's after 360 that the graph forms a circle. That's it. This is half of a circle, and this is half of a circle. Remember, we said the total angle in a circle is 360 degrees. So when this is 360, and this is 180, and this is also 180, making a sum total of 360 degrees. So after 360 degrees, the graph continues projecting itself to this direction until it gets to another point that is 180 added to it, which is at 540. It reverses again, gets to at every 360, the graph forms a circle. That is the meaning of it is periodic at 360. The length EAE, so this is our A and this is our E, this another A, this our E, is called the amplitude. I've explained it. That is the difference between the point, the average, and the point of maximum displacement, or the average and the point of minimum displacement. So this is the nature of the sine graph. Now let's go to the cosine graph. The cosine graph also behaves like the sine graph. The graph of y cos theta can be drawn in a manner similar to that of the sine theta, except that the angles are measured from OR in the clockwise sense. This is so because cos theta is equals to sine theta minus sine 90 minus theta. So essential features of this graph. Now what it's trying to tell us now is that, remember, when we did the sine graph, the graph started from the origin. We have something like this. We had something from here. This is the origin, the 0 point. The graph started from here, came to 180, started moving at 360, 180, this is 90, this is 270. But the difference now is that the cosine graph did not start from 0, but rather it started from this point and came down to 90, climbed at 270. So the point that was not touched by sine graph are the points that you touch in cosine graph. So 180 will be empty, 360 is empty, so the graph is coming down again to this point. It's coming this way. It also moves as a periodic graph. That's how it continues projecting. So the difference between the cosine graph and the sine graph is just that the sine graph is leading the cosine graph by 90 degrees, because the sine graph, the first point was 180, while the cosine graph, the first point is 90. So that is to say the sine graph leads by 90, while the cosine graph lags. We use the word lags by 90 degree. In addition, the cosine curve lags behind. Okay, it has been stated, curve by a difference of 90 degrees. The difference is usually called a phase difference. So the difference between the 90 degrees of the cosine graph and that of the sine graph is called the phase difference. In other words, the cosine graph curve lags behind sine by 90 degrees, of which we've done justice to that. Now, the difference now is the tan graph. Remember, in our relationship, we once proved that tan theta is equals sine theta all over cos theta. This was, we did justice to this in our previous lesson. Tan theta is equals to sine theta over cos theta. And if you watch the graph of tan theta, the curve consists of 3 parts between 0 and 360. So this graph, it continues this way. Let me project it. So the graph continues this way. The tan graph has 3 different parts. This is tan theta. You have the first part at 360, you have the second part at 180, and you have the third part at 0 degree. This is the nature of the tan graph. It is not a periodic graph like the sine and cosine that usually move in this pattern. The angles are separated from each other. So the curve consists of 3 parts from 0 to 60. You can see the 3 parts: 1, 2, 1, 2, and 3. Since the tangent function is not defined at 90, remember tan 90 is not defined, and 270, the function is said to be discontinuous at this point. Now, one of the things I'd like you to do is, before you continue with this, can you just consult your calculator and check the value of tan 90, check the value of tan 270. Then you understand why this curve did not pass through this point and did not pass through this point, because it does not exist at this point. Now, the curve rises and falls rapidly at angles very close to 90 and 270 respectively. The curve approaches the vertical lines at 90 degree and 270 but never touches them. These vertical lines at 90 and 270 are called, the vertical lines at 90 at 270, that is, these vertical lines at 90, you continue like this. This is 270. If this curve should go this way, you still have it at this point. So these vertical lines, the straight line that is formed here, is known as asymptotes. We call them the asymptote of the tan graph. So I think with this, we've come to, we're almost done with identifying the nature of the sine, cosine, and tan graph. Now, this is the relationship between the sine and cosine graph. Now you discover that both curves, now look at what is going on. Both curve, that is this for sine graph, this for cosine graph. Remember, I said, we stated earlier that they are both periodic. They are both periodic. This was what we stated. That is, they move in a sinusoidal form, up, down, and this is that of cos, up, down, up, down. Now, another thing you should notice is that sine leads the cosine by 90 degrees. That is to say, now they started from here. Look at when they started touching the line apart from the zero arc. When sine is at 180, this is sine graph. This is where cosine is. Cosine is at 90. When sine rised up as 360, cosine is at 270. So sine leads cosine by 90 degrees, while the cosine lags behind by same 90. And the both look like a wave. This is the nature of a wave. You can call it a sound wave. Example of waves that look like this is we have the sound waves. We also have the alternating current, like if you're talking about the simple AC circuit and so on. So this is just all about the sine and the cosine graph. I would like to say thank you for joining us in this section. But if you really want to refresh your memory on what we've just discussed, please take the text that will appear on your screen. That will serve as our strength in you understanding more on what we've just been taught. But also do well to use the lesson notes on the platform for a better information on the topic we've discussed. Feel free at all time to drop your comments and questions on the comments section. We'll be very glad to hear from you. Thank you.